Here's our next example. Again, we're still working with a converging lens. The focal length is 25 centimeters. It's positive focal length because it is a converging lens. We have now placed our object inside the focal point, meaning closer to the lens than the position of the focal point. And so where will the image appear now? Well, let's try our ray diagram. The first ray, always the same. We draw it parallel to the normal until we hit the lens. And then when the ray goes through the lens, it diverges or refracts and continues on through the focal point on the other side. So that's ray number 1. Ray number 2, we draw from the object through the focal point to the lens, to the focal point on the same side of the lens. And of course, that's a problem because we're already past it. But just like we did with the mirrors in the past, we draw a little line from the focal point to the top of the object, then continue with that ray this way until it hits the lens. And of course, at that point, it's going to refract or bend, and it's going to continue on straight this way. And so that's ray number 2. Now you can see that those two rays do not converge. They do not come together behind the lens. They do not form a real image. But the observer on the other side of the lens sees those two rays coming in these directions. The brain kicks in, says, oh, I know where they came from. This one came from back here somewhere. Because remember, the brain has no idea that the ray did some bending here in the lens. It just simply appears that it came from back here. And the brain will interpret that this ray here came from back here somewhere. And where the two rays appear to be coming from a single point, that's where the brain will form an image. It's not going to be a real image, it's going to be a virtual image. Let's see how that works out for us when we use our equations. All right, so S prime is equal to SF over S minus F. And S is the object distance, which is 15 centimeters. The focal length, 25 centimeters. There we get 15 minus 25. Notice that the denominator is going to be a negative quantity. So this is equal to, looks like 375 divided by a negative 10, which is a negative 37.5 centimeters. All right, so we found our image. It's 37.5 centimeters from the lens, but since it's a negative quantity, it places it in front of the lens. So this distance right here is 37.5 centimeters, but the negative here indicates that it's in front of the lens, meaning it's a virtual image. So that's it. That's why we can write I is virtual. Okay, now for the magnification. So M is equal to minus S prime over S. So minus A minus 37.5 divided by S, which was a positive 15. So this would be a positive 2.5. So what that means is that the magnification, the size of the image, is 2.5 times the size of the object. So the image is much larger than the object. And since it's positive, we say that the image is upright. And this is really an example of how a magnifying glass works. If an observer looks through a lens, that's a converging lens like this, and an object is placed closer to the lens on the focal point, the observer will see a virtual image on the other side of the lens that looks a lot larger than the object. And that's exactly what we do when we use magnifying glasses. This is also the way reading glasses work, and later on some examples will show you how we use lenses for vision correction. And so this would be vision correction for someone who's not very good at seeing things up close. We use it as a magnifying glass so that it makes the image larger and easier to see. All right, so again, summarizing, the distance to the image was 37.5 centimeters. The negative indicates that it's on the other side of the lens from the observer, meaning on the same side of the lens as the object, which makes it a virtual image. The magnification, 2.5 times the size of the original object, and since the magnification was positive, we can say that the image was upright. And that's how we work with converging lenses.